Thanks, Sasha, for the invitation. And this is an opportunity for me to talk about a project that has been going on for quite a while with a lot of collaborators. And it's looking at the offshore, the east coast of the United States, at potential rift basin storage locations, storage reservoirs. So it's a bit more of a exploratory talk, a little more exploration rather than monitoring, although everything Jonathan talked about was and would be incredibly useful and essential if this were to be a storage reservoir in the future. So a lot of this work has been collected in sequential projects, not just one project that were funded by the U.S. Department of Energy. There were even earlier projects on land projects funded by the National Science Foundation. And as I said, a lot of collaborators have contributed to this sort of composite study. And I will start today with a quick discussion about carbon storage and basalt. Unfortunately, I was counting heavily on Chiara to present the CarbFix project, which is sort of a landmark opportunity to explain how that works. I'll do a poor job of trying to imitate her, but we did work on that project together, so I'll be able to at least give some background of why we're looking at basalt. Then we'll look at the East Coast U.S. rift basins in particular and move then to the East Coast offshore area and its CO2 storage potential, and then some ideas about where we can, what we know and where we can look to improve this opportunity in the future. All right, so first and foremost, we're looking at putting CO2 in geological storage formations below ground or below the seabed. There are, for simplicity, just say four mechanisms that keep CO2 underground. Primary trapping, which is essentially pumping CO2 below into a reservoir rock below some capstone, and it is impermeable and physically maintained below in the reservoir, since CO2 injected in liquid or supercritical state is buoyant. So that's illustrated here in this figure, but over time, there are at least three other significant mechanisms that contribute to keeping CO2 in the ground. It dissolves in the water in the formation, becoming more dense. It gets caught in small pores in the formation, capillary trapping is sometimes called. And importantly, it over time in reactive rocks, such as basalt rocks, it gets mineralized into from liquid carbonate, from liquid CO2 into dissolved aqueous state CO2, and then into solid form carbonates. So these are all a variety of mechanisms. They all play a role in the CarbFix project, which this is an illustration of. That's actually on the poster for the talk. This session's talks come from the CarbFix project. Kara and I worked on this together. And it basically illustrates on the left-hand side what the CarbFix program project is doing and continues to do, which is pumping water out of the subsurface aquifer, joining it with CO2 captured from a power plant or from direct air capture facilities on land, and re-injecting dissolved CO2 in the ground. That's so the red track and the blue tracks combining to make purple. And then over time, that is a dense plume that carbonates, reacts with the basalt and carbonates into minerals in the subsurface. Very, very successful. I would encourage any of you who want to learn more about and see more about the CarbFix project. There was a couple weeks ago a CarbFix summit that was recorded, so I think there's a lot of talks about the initiation of this project and its success online still. So the idea here is to move this concept offshore and expand both the reservoir potential in offshore basalts, illustrated on toward the right side of this figure, potentially also utilizing the vast resource of the ocean seawater to dissolve CO2, or at least to inject into seawater-filled aquifers that are basalt rock by nature. And these are reactive, right? So this adds the component of all four of the trapping mechanisms that I mentioned. So there have been two primary basalt projects where they've been illustrated to capture in pilot experiments. One was in, I just mentioned, the Carbfix project. The other one was in the Western United States in the Columbia River basalt. Here's an illustration of or picture of the Columbia River Gorge with layer cake basalt flows. And I borrowed from Cassie Davidson. It's just an illustration of with the white bars of flow interiors that are sequentially layered on top of one another, interspersed by flow tops or flow contact zones. And it's very obvious just from the green and the biological life that the interflow zones are the ones that have fluid flow. They degrade and basically alter over time and essentially support plant life when they're exposed to the air. So this project is being repeated essentially in the near future, looking at a pilot injection in these rocks. And these are distinct from the different kinds of flows that occur in the ocean bottom, as well as in a volcanic setting, right? So there are different kinds of basalts. The concept here, though, that I'm looking at in particular in the rift zone context on the east coast of the U.S., this was in fact a rift zone in 200 million years ago with the opening of the Atlantic. It's illustrated in the sphere on the bottom right, and it was more or less coincident, or soon thereafter coincident, with a massive flood basalt, not unlike the Columbia River basalt that extrusively put in the Central Atlantic magmatic province, and that's illustrated. You see in the gray areas in the sphere. Over time, say 200 million years, we now have the east coast of the U.S. Those basin outcrops from that rift basin contain rift strata, including basalts, and the dark images sort of near the box labeled A, and in between A and B are the exposures of those rift strata on land. They contain basalts, they contain sand shale sequences, and there are a number of them illustrated in grays that are not exposed at the surface, and those are the ones we're going to be looking at a little bit more closely. And in particular, in the A box, I do have a pointer here. In the A box, the dark rift basins are the Newark Basin, looking like a banana here, the Hartford Basin, and then a couple of these offshore gray basins where we're going to look at in the Northeast area in more detail. So I happen to be right now by the capital letter A, talking to you, and we're sitting at the upper northeastern corner of the Newark Rift Basin on the Palisades Sill. And about 30 miles to our southwest, there are a series of basalt flows called the Watchung flows through the rift graben that we've been able to both image seismically and have cored over time. And that has illustrated that there are discordant flows throughout this basin. You can see this is the Palisades Sill, which outcrops right near me, as well as these Watchung flows, which are shallower and outcropping to the left. This is on the right, a schematic of the full sequence of the rift graben with deep water and shallow water lake basin sediments, as well as one or more flows illustrated in red. Just note here that I have one flow and two flow scenarios as a marker for another slide later in the talk. We'll come back to that. On the left, you see a picture of the Palisades Sill, and it's pretty massive, right? So this would be, although it's a sill, something equivalent, at least in terms of the dynamics of it for injection, a flow interior. The Watchung flows, we were fortunate enough to be able to drill through. So this is one of them called the Orange Mountain Basalt, and the contacts between the Orange Mountain Basalt flows have a flow top and a flow bottom that is high permeability, porous, fractured, illustrated by the box of cores at the bottom, and in between, massive flows that are impermeable and dense. So we have full core from this from these drill sites that were recovered several decades ago, actually, but are still available. We also have a full suite of geophysical measurements in these wells. I'm illustrating that here on the left. You can see a few of the measurements, porosity in particular, different porosity measurements, density and neutron, and core measurement porosities over the orange mountain basalt, which is a 500-foot thick layer, and that the flow top is a 50-foot thick layer, highlighted in gray. All of the porosity measurements illustrate significantly higher porosity in the flow top. And looking at a blow up in a very, very low tech methodology here of the porosity estimates over this zone, there is pore volumes that in just the flow top, in just the orange mountain basalt, that are between 1/10 and 1/3 of a cubic kilometer of pore space. So a fairly large amount that, depending on how efficient carbon dioxide could be injected and stored, would amount to, say, 10 to 30 million tons of potential resource for storage there. That depends on several assumptions. However, it is very clear from all these measurements that at least within the flow tops, there's easily a 100% increase in the porosity of these rocks over the interflow zones. So one other measurement on land that was made about 15 years ago by our colleagues at Pacific Northwest Laboratory was when they were looking at the Columbia River basalt, was to compare it with other basalts in terms of their reactivity for mineralization with other basalt flows around the world. So we see the Karoo and Deccan basalt flows in green and black from South Africa and India. The Camp in light or blue here, which is actually the southern South Carolina southern basalt flow, and then the red is the Newark Basin, technically actually the Hartford Basin. And what this illustrates are incubation tests of CO2 and samples over a couple of year period. The more CO2 pressure is in the incubator reactor, the less reactive it is. So when CO2 pressures drop, basically the rocks are being dissolved, and carbonates are dissociating. So what the takeaway here is that the most reactive rocks are those from the basalt from the Newark Basin or Hartford Basin area by a significant amount. So this is was explained at the time by having greater basalt glass content. That could be part of the answer. But the motivation for looking at basalts, in any case, as a reservoir, as a mineralization, as a storage reservoir that will mineralize, is significant, and that draws us to looking offshore. And this is a map from the early 80s, from using data that was recorded in the 70s, looking at the Hartford Basin, near the Hartford Basin in the north, the Newark Basin to the west, and somewhat analogous offshore basins called the New York Bight Basin, the Long Island Basin, and the Atlantis Basin in particular that we'll look at right now. And looking at seismic data, which were recorded at the time. This is 2D, very low res seismic data. And a project that was developed. Oh, this is what seismic data is for those who may not want a quick refresher. It is a method to, especially offshore, to look at surveys below the seabed. But I want to point out, as Jonathan did, that this has been the backbone technique for both reservoir exploration and CO2 monitoring over time. Whether it will be part of the equation, but it doesn't have to be the entirety of it, of course. So looking at this area, a project that was built about 4 or 5 years ago, looked at the reservoir capacity on the Rift Basin itself. These kidney-shaped features or areas are sediment targets, and with some drill holes, which are illustrated by the little dots, as well as a lot of seismic lines that are illustrated in yellow. What I want to point out is among the various goals of this project, there were a key interest, certainly of mine and others, was to refine the Rift Basin locations, their extent, and their infill on the Long Island platform, which is that central area in between. So we were able to reprocess, essentially using modern techniques, to improve those images. And you can see here a color image of the unprocessed, or original, I shouldn't say unprocessed, the original data that was interpreted to create the map on the left. A little section in red is this cross section in the color sequence where we see a rift graben or half graben that's filled with relatively poor resolution. Below a breakup on conformity and about 800 meters of overlying sediments right there in the Long Island Basin. What we're able to do, and I'll sweep through about 3 examples of these cross sections before and after of seismic without going into too much detail, just to give you a sense of what it looks like. I think. Not forwarding. There it goes. Okay, so this is the same section before on the top with legacy data and reprocessed data on the bottom with much signal to noise improvement, as well as characterization of the reflectors that is not modern age seismic capabilities, but more interpretable than it was in the past. Secondly, looking to the southwest, the New York Bight Basin, which is this long line from the New York Bight all the way out to almost to the shelf edge. This is just the reprocessed data here, but that has illustrated a couple of interesting things. That was what was identified early as a basin may not be a basin or a very shallow basin at all on the northern side of the New York Bight. There is much better characterization of the basin, of the Rift Basin that's buried to called the New York Bight Basin, and in fact identification of a new basin that's shallow and sitting to the on the outward end of this section, illustrated on the in yellow. But this was named by a colleague, Will Fortin, as the Dante Grande Basin. You'll see why in a second. And lastly, the last example I want to show is this section up near the Atlantis Basin near Nantucket, where the characterization of those deep basins are much more well defined, as well as the structure of it, as well as some of the characteristics inside the basin, both inboard and outboard of the seismic of the shelf break. Okay, so together, just to put this sort of wrap this up, these basins were reinterpreted. Those are shown in pink. The old basins, the old interpretations, are the outlines in green, and obviously the seismic data used to collect that information is shown in orange. This is the new basin called the Dente Grande Basin because of its unique characteristic shape. And then these are the characteristics or the outlines of the other basins as refined by the new processing. You can see obviously that they are larger and more elongated in northeast-southwest direction, consistent with the northeast-southeast rifting. And in particular, I want to highlight the 3 basins that are near shore on the shelf, highlighted on the right in pink, and a cross section of one of them shown in black. These 3 basins are now targets for a new pending proposal to look at an aeromagnetic survey and to model what the infill of these basins contains. Is there any basalt in them or not? And I believe we convinced ourselves, and hopefully convincing our funders, that this is a viable solution. Aeromagnetic surveys, and just to give you a quick primer, basically faults and basalt rocks will alter and distort the Earth's magnetic main magnetic field. And when you drive an airplane across one of these features, you will see anomalies that you can interpret by forward modeling of what that signature will look like. So with a well-designed grid of aeromagnetic surveying points, you can determine a lot about what is potentially in or below the surface. So we did that and modeled, and if you refer back to the stratigraphy of the Newark Basin, we had a one basalt flow and a 2 basalt flow model, and obviously we'd have a 0 basalt flow model as well. And we were able to convince ourselves that there's, with reasonable assumptions, significant aeromagnetic or magnetic signature that we would see across this basin. Both the width of the basin, if it were filled with a 1 basalt flow or a 2 basalt flow of a known thickness, We can determine the difference between them and distinguish between them. So we could see one or a two basalt flow or a no or a zero basalt flow, if that were the case, and from various altitudes for a survey. So we're doing some due diligence here that in fact there is a signal that we would be able to determine in these offshore basins that would identify a basalt flow that we are making the assumption are similar to the basalt flows in the other Mesozoic basins that we see on land. So why do we care about this? Well, in the offshore region, this is some work done by colleague who at the time was at Rutgers, John Schmelz, and he did a survey of basically all the natural and coal-fired power plants in the region, a strong concentration, of course, on the coastline in the New York metropolitan area and across the Appalachian Basin. He also did a study here for power plant source CO2 emitters that the additional cost, if you will, for transporting that CO2 to the offshore environment was relatively modest compared to the challenges of injecting CO2 in reservoirs local to their origin. So I call your attention to that paper if you're interested in that kind of work. And I want to point out another motivation, and I find this to be very compelling myself. This is a repeat of the reprocessed or the identified images of what we think are the rift basins, the Mesozoic rift basins offshore. The red stars are the samples that we have collected of the salts on land. I note here, this is the Newark Basin one. There were basalts drilled on Nantucket, so it is not complete fantasy that in fact there are basalts in these buried basins. And indeed, the location of these basins, what I want to point out here, if you look at the BOEM, that's the U.S. Bureau of Offshore Energy Management, who issues lease blocks for both oil and gas and other exploration, as well as for wind lease blocks. The Empire Wind, Sunrise Wind, and Beacon Wind lease blocks that are being developed overlie very closely to the locations of these Mesozoic rift basins, and the planning areas for new lease blocks span between them. So the coincidence of just the infrastructure build out and the opportunity there to do two things in concert makes a whole lot of sense to me. Okay, so just to conclude, I don't want to take time. I want to leave some questions and discussion opportunities. Of course, the work we did in that project to look at legacy seismic data indicates that, for example, the New York Bight Basin is likely smaller than previously thought, that the Long Island Platform and Atlantis Basins are larger. Atlantis Basin are larger than previously thought. And that with further research, and this concludes magnetic surveying, as well, ultimately, as of course, drilling and sampling, that those buried rift basins would provide opportunities for in situ mineralization in basalts if they are indeed identified and present, like they are on land in the similar aged basins. And that it is time now to think about this in a coordinated way so that reservoirs, either the offshore Mesozoic basins or even just offshore reservoirs at all, that infrastructure for that can be built out with the offshore wind build out as well. I think that's my last slide, so I'll stop and take questions. Happy to do so.
Thanks a lot, David.
Yeah.
If you have a question, please raise your hand or type it in the chat. Julia, please go ahead.
David, do you have an idea of what the interest from New York or New Jersey is in storing CO2 offshore?
Yes, I think I can answer that. Let me go back onto screen here so I can see so those are three of those projects were funded by the U.S. Department of Energy. Okay, so that there is interest certainly in storage opportunities in the area. There is a strong interest, of course, in the wind build out, right? So offshore infrastructure is there. The need to put together regional, I think the important takeaway for me anyway is that a regional solution is needed. And there is definitely statewide, multiple statewide interest in doing so. Regional partnerships in the Northeast area, Maryland, Delaware, New Jersey, New York, Pennsylvania, Michigan are all regionally connected to try to do exactly what we're talking about. There hasn't been a whole lot of study, some, but not entirely offshore. Most of it has been looking onshore, but it does run up against a bit of a roadblock, right? When you're looking at onshore sites, because we don't have, we don't have depleted oil and gas fields, right, in the New York area. So yes, so I think the interest is there, and we're just sort of building out the rationale and the confidence in it.
Derek.
Hi, thanks for the interesting talk. I was wondering, for these, say, for example, these basalts in the Newark Basin, is the porosity mainly fracture porosity or kind of just regular rock porosity? And do you prefer one or the other for the CO2 storage mineralization?
Yeah. So that's a great question. So the porosity is both. Basically, those flow tops are points in the evolution of the flow, in the series of flows that were when they were in place, where the rocks degas and create bubbles, so you get this high porosity zone, and then a subsequent flow comes across on top of it and breaks, thermally fracks it. So you get both, and these interflow zones are highly permeable and high porosity. The question is, it's hard to say without looking at the specific core whether one dominates the other. But as long as it's contained above and you don't run into a vertical transecting fracture, I think you have surface area that you can inject into and react with, I think you don't really have a preference. Yeah.
Thanks, John.
So I was intrigued by your comment about co-location of wind farms and CCS complexes. In the North Sea, there's a lot of tension at the moment between developers of wind farms and CCS, and the fact the UK government, the UK regulator, is being reviewed, but currently says that wind farms and CCS sites are not compatible, and that's around the problem of shooting 3D seismic through wind farms. So I wondered whether that had been discussed stateside.
I'm aware of that. It wasn't. I haven't heard the 3D seismic piece rationale. It's interesting. Basically, I think the first step is just getting those two entities to talk to each other about what's required, and it doesn't have to be identically located in a specific geographic GIS coordinate system, but in general, the build out and the maintenance and the workforce and the capacity to deal with any kind of industrial development in the coastal area should be coordinated, right? So it doesn't have to be literally the same spot, but I do know that there's some activity in Norway looking at exactly this kind of thing. Yeah.
We have two more questions, or three. Let's start with Kim.
Hi, I just have a question. Is there any appetite for either reshooting some of that seismic, maybe even 3D, or doing CSEM?
Yes, and please. Yeah, the seismic is is pretty vintage, right? So we did the best we could. It certainly could be improved quite a lot, and I think the next sort of low bar is looking at just the geopotential measurements to see if there's a signature that gives us hope for a basalt. I mean, there are the rest of that study, which I didn't really talk about, is looked at some sedimentary reservoirs in the region that would be potential storage as well. So doesn't have to be the only solution. And there's a bunch of legacy data that was just released, mostly 2D, in the area as well, but not in that area on the platform where those buried rift basins are. So, but yeah, that'd be great.
Zoltan, please.
Hello. That was a really nice talk. I really enjoyed it, and I hope I've learned quite a lot about it as well. Now, I have some kind of basic questions about the efficiency of this process. So, how can you sort of fill up a reservoir like that with CO2, a basalt reservoir with this reaction? Does it petter out how much it can take, and how would that, so if there is, I assume there is like a higher limit of how much it can take, so how would that relate to how much CO2 it would cost us to actually build out the infrastructure and start using that as a reservoir and keep using that as a reservoir?
Right. So this is where we are really missing Chiara's talk to lead into this talk, because the experience that they have at the Carbfix site has been that they have been injecting for a number of years now in a basalt mineral reservoir. It's been progressing well. They have been able to monitor it and have as high as 90. In early studies is 98% mineralization over a relatively short period of time, but it doesn't seem to clog itself up. The injection, at least the style of injection that they use, which is dissolving the CO2 in water and then injecting the dissolved fluid, progrades the dissolution front and the reactivity front outward and fills up the reservoir without back pressure, without having a problem, at least so far. And they've done tens of thousands of tons of CO2 injection at this point. Okay, so that's been pretty successful. Whether that is everywhere successful at all volumes over many decades, we don't know yet. All right, there's only been 2 experiments done in the field to date.
Right.
And I don't, sort of the life cycle question, I'll have to defer that. I don't really know.
Yeah, all right, that's fine. Thank you so much for the answer.
Mm-hmm.
Okay, one last question by David, please.
Hi, good afternoon. I think you may have answered part of the question with the previous one. I'm sorry. I wasn't able to catch the talk since the beginning, so my apologies if I'm going to ask something that you mentioned. But do you have the boreholes crossing those offshore basalt units that we're talking about? Or are the estimates for the basalt derived from some other outcrop areas or some other regions? And if you have samples from drilled basalts in the offshore, are they valid to apply to some other undrilled basalt units?
So we have just the opposite, unfortunately. We have basalt cores onshore.
Okay, yeah.
And we believe that they are the same age, the same nature, the same flow, the Central Atlantic Magmatic Province flow that would fill these buried rift basins as well. So we're making that assumption that those are relevant. Those are the tests that have been done, the samples that we've looked at onshore are the same reactivity, the same type of material that would be offshore. The only data we have on the offshore environment at this point is the legacy seismic, illustrating the extent and position of those basins, which has been evolving. I think the next steps will be more geophysics to survey the area, become even more convinced that there are basalts in those basins buried. That's our hypothesis. And then the next step after that would be certainly to do exploratory drilling. Now, the good news is it's not very deep water. So exploratory well there is probably a manageable first order research project to do. Certainly not, it's not $1 billion platform, for example, in deep water. So those things could be done to test the reservoir. And then you would, of course, have the samples. You would have to do well testing and do all the things you would do to characterize any reservoir. But we're not there yet. So this is forward future projects.
I think we all suffer from the same problem, isn't it?
Yeah, it's the same everywhere, right?
Thank you.